Henson and I'm a PhD researcher at the University of Manchester. I'm here today to talk about how to build a universe, and that's actually what I do every day. I build model universes on a computer. So all of our ideas about the universe are based on the fact that the universe began in this Big Bang, where it started off in a really small, dense state and then expanded outwards rapidly to form what we see around us. And we know that just after the Big Bang, this light was emitted that's been travelling through the universe ever since. When you look at it, and I've got a picture just here, you can see that there are kind of areas that are brighter and the areas that are darker, and that's what we show as red spots and blue spots. That pattern, which kind of looks like a bad paint job, actually reflects what the universe looked like just after the Big Bang. Now, we can't actually see it with our eyes because it's not the same kind of light that we can see with our eyes. It's actually microwaves. So the way we model it is we take a box of some size. We say, I want to model some portion of the universe. And we know how matter is distributed through that. So we say, I'm going to create some particles. And these are not particles like you know them as really tiny things. These are they're just things that are going to tell us roughly where stuff is. So they're really, really massive because we're on big scale. And these particles are going to be spread across our box. And they're just going to tell us roughly where things are. So we've got our starting point at the beginning of the universe. Kind of looks something like this. Those little blue points, they're all the particles. But again, remember, they're massive. So this box is actually huge. But real things in the universe move. And we get movement from forces. So that's the next step, is getting things moving. So the most important force in astrophysics is gravity. So the way we figure out how they're going to move is we take each particle, and typically in a box this size, we'll have something like 10 billion particles. We'll just take one particle, and we'll take another one, and we want to work out the gravitational force between the two. Now, we can do this just from Newton's law, which is enough for this, and that's the same law that describes, you know, if you drop something, how it will fall to the ground. So we take these two particles, we can work out the force between them, and once you have a force, you can get an acceleration, which tells you how it's going to move. Then you have to work out the force between your particle and the next one, and the next one, and the next one, and you do that, whatever 10 billion minus 1 is, and eventually you've got the force on that one particle. But now you need to work out the force on all the other particles as well. So you then go to the next one and do the same thing. And once you've done all of that, you'll actually know how your particles are going to move. So you take them all, you move them all a little bit. But the problem is now that force has changed. So what you have to do is only move them a little bit, then do all the calculation again, then move them a little bit. You do this a few million times, and eventually you get to the present day. So the next most important thing to put in is the way gases behave. So we know that when steam rises from a kettle, it will expand and it will cool. Now what physicists do is they take that behaviour and they just write it as equations. And it's the same understanding, just presented in a different way. But if you can write it as an equation, you can include it in your model. So what that means is that when this gas in the universe is really, really hot, it will just expand and cool, as we know that it would. So that's another force in our model. And so this picture here shows you what the universe looks like if you have gravity and you have the way that gases behave. But that's not quite everything, because we still don't have stars, and we still actually don't have black holes. So how do we create stars? So the way we do this in our simulations is when we see some gas that is hot enough and dense enough that it would normally form a star, we just get rid of that gas and we create a new particle that's a star particle. It's a bit of a trick, but at the moment it's too expensive computationally. Now, we don't necessarily know the details of what happens at a black hole or when you go through a black hole, just because it's so different to our own experience of the universe. But we do know how it affects the things around it, and that's what matters if you're trying to model something. So if you have a black hole, so you have this really dense, massive point, it will slowly pull in any matter around it through gravity, and it will orbit it in what we call an accretion disk. So it's a disk, and it will eventually fall in. So we can add that into our simulations so that our black hole will swallow anything and it will get slightly more massive. So we see that some black holes have these huge jets of material coming out of them, and those big plumes will just collide with anything around them. So they affect the larger scale of the universe. So we have to include them. So now we've got in our models, we've got dark matter and gas that interact through gravity and through the way that gases behave. We've got stars, we've got black holes. There's a lot of stuff we don't have. We don't have planets, for example, or comets or asteroids. But we actually think that if you care about the universe on really big scales, which is what we're studying here, that stuff is not as important because it doesn't affect the things around it. It's still interesting, but we're not quite there yet. So, does it work? Well, let's find out. And one of these is a picture of the real universe taken by the Hubble Space Telescope, and the other one is from a simulation, from a model. And if you look at it on a more scientific level, so you look at the properties of the galaxies themselves, you find that we're almost there. Now, that doesn't mean we're done. We're going to continually improve them as we learn more and more about our universe, but we are getting. This is really important because not only does it help us to learn new physics and to understand our universe better, by tweaking and changing our models, we can figure out what gravity is really like, for example, what this mysterious dark matter is. But it also means that we can test all of our methods for observing the universe. So if you plan to have this, huge telescope mission, you want to know that all of your analysis is right. And also it means that everyone else can trust your work. So simulations are still playing this huge role in astrophysics, and they will continue to as we go forward.